Hi everyone, welcome to another episode of Mr. Carlson's Lab. Today we are going to electrically restore and align a B&K Dyna-Jet Model 707 vacuum tube tester. Great tube tester to own. This is a dynamic mutual conductance type tester, so a little more thorough than just an emissions tester. There's a lot of these things out there still. There's B&K Dyna-Jet 707s and the 650s and all of these models still floating around out there, and they're pretty plentiful. So if you're thinking of getting a tester, I would think pretty hard about getting this particular tester because it is a really good tester. I've had probably 4 of them, and every time I end up restoring one, somebody talks me out of it, so I end up getting rid of it, and then I get another one and restore it, and this is this thing. So I think I'm going to hold on to this one here for a while. So at any rate, let's get into this thing. I'll get it up on the bench here, we'll take the whole thing apart, and I'll show you how the thing works. Let's get started. Alright, so here is the B&K Dyna-Jet in its case. The case on this one is in surprisingly nice condition. A lot of the time when you find these testers, the cases on these things are pretty rough. So this has just got a few nicks and scratches, nothing that couldn't be most likely touched up to make look just a little bit better. I haven't done anything to this thing, so I picked this thing up and this is the way it sits. So they open up like an old suitcase. Little chart here, we'll take a look at that in a moment. It's hard to fit this all in the frame. This one here has the manual with it still, which is very, very nice. And the overall condition of this particular tester physically is very, very nice. Electrically, I have no idea because I haven't taken this thing apart or done anything with it yet. Now, if you're going to buy one of these testers, one of the things that you're going to want to look for is cracks in the meter face. A lot of the times, these things have got a crack and they're just very badly damaged, and it's from just abuse from these things being thrown in and out of a service vehicle way back when. And of course, this is a kind of an odd looking plug. It has a little thing here so you can quickly unplug it, right? Well, if you put this back together and this accidentally sits like this, say this is sitting straight up, and then you slam the lid down on it, you're going to crack the meter face, or even worse, it could be the other way around. So very, very common. So if you're going to purchase one of these things down the road, that's one of the things that you're going to want to take a look at. Make sure there's no cracks in the meter and make sure that the meter actually does operate correctly. So there's a cap here as well that plugs in. All right, so that's very important to have. So you want to make sure that you have that. Of course, it'd be easy to build one if you didn't have that. And all the manuals for these things are quite readily available. So if you look down here, so the top of this thing, I'll move you up here just a moment. So it has a chart here, and you can move the chart around. It's just held in by this little clip down here, and you just pull this out. So all the tube reference settings for this thing are all on this chart. There's a lot of them on here, and that's one of the reasons why they called it the Dyna-Jet. I'll talk about that in just a moment. So there's the charts are up in here. Now, in order to get this off, is what I'm going to show you here, is this here just slides out. So these pins just slide out like that, and then you can very comfortably remove the top. And you can put this off to the side and flip the pages if you need to look up some particular tube. So you move this out of the way, and you've got quite an extended list of tubes to test here. So it tests a lot of tubes. Now they make this somewhat quick to set up. So this down here. And I'll zoom you in. So you can see the heater control right here. So these are all the voltages for the heaters that you can set up. And a sensitivity control right beside it. Now if you look at the tube sockets, you'll see, like it says here, 6AU5 71. All right, so if you're going to plug a 6AU5 into this socket here, obviously since it's a 6AU5, so you would set the heater control here, back this out, you would set the heater control to 6. Now you never plug the tube in before you do this, because if this is sitting up at 50 volts and you plug a 6-volt tube in there, it'll light up like a light bulb. So you set that to 6 first. It's kind of hard to see on an angle. And then of course you would set the sensitivity up here to the appropriate number. Again, if it's a 6AU5, it says 71, so you'd set this to 71. You plug your tube in and away you go. It's just that easy. And they, put most of the common tubes up here. So lots and lots of tubes. Now, of course, there's a few tube sockets in here that usually get worn out. The ones that, you know, test the 12AU7s, 12AX7s, and 6L6s and stuff like that are the tube sockets that, you know, get worn out in these particular testers. But if you find one of these that is, you know, in relatively good condition, it may be, you know, a low mileage unit. If not, you can find these sockets around. Instead of replacing the entire socket, the best thing to do is go onto the rear side, desolder the wires from the, you know, the actual lug on the bottom of the socket, and pull the, you know, the wrecked pin out, and then take a good socket and then put another one in. That way you don't destroy the actual tester. So I see that a lot. A lot of people drill these rivets out and then put, you know, brand new tube sockets in there. There's no need for that. So you can repair the sockets that are in here. It's just a little bit time consuming, but you know, it's well worth it to preserve the, you know, the appearance of the actual tester, because it is actually a very nice looking tester. So it has an extended test down here for different types of tubes. So, and that's in these charts here, right? So you'd set all of these up to the particular type of tube that you're going to test and then plug it in, of course, setting everything else up. In order to use the tube sockets down here, you have to transfer this over. So this pops in and pops out. You see that? So when it's pushed down and popped in, instead of testing up here, now you're testing down here. We have test 1 and test 2. So many tubes have got 2 parts inside them, like say a 6SN7 has 2 similar triodes inside. So you'd have one test for one of the triodes and another test for the other triode. It tests for grid emission and shorts. It's very, very sensitive. Again, this is a dynamic mutual conductance type tester. So, you know, one of the better types of testers there are out there. They've done a couple of neat things in this circuit as well here, so you don't have to, you know, set up the line voltage and things like that as well. All right, so in order to get this thing out, it is not too tricky. So I'll move this out of the way, get this manual out of the way here. So you just have to remove the screws on the perimeter. So we have a screw here, a screw here, and all the way around. And they've hidden one on the back. And I notice a lot of people bend these things up because they don't know about that one screw. So there's a very heavy transformer inside this thing. And they have this one screw on the bottom side, and you can't forget about that. So I'll move the focus over here. So what I'll do is I will put this in here. So with all the screws, this little ring should come off. It does. Everything is falling on me here. So with the screw still on the top side, it's okay to undo this. I would undo this one first. That way it doesn't all fall out. So now that that one's out, when you undo all of these screws here, what you can do is very carefully flip it over and remove the backside if you like, or like what I do is I usually just grab this knob, give it a bit of a pull, stick my finger under the lip, and lift this thing out. So it's a very easy process. So what I'll do is I'll undo these screws, I'll save you from all that, and I'll lift this out of here, and we'll take a look at what we're up against here. All right, all the screws have been removed from the perimeter, so usually what I do is I just grab this one knob, you'll see this corner lift, stick my finger under it, and lift the whole thing out. As you can see, the whole thing will just come out. So it's a little bit awkward to do on camera. So what I'll do is I'll just lift this thing out of the case here, and I'll turn it upside down. We'll see what we're up against on the back side. This is what the tube tester looks like on the bottom side. As you can see, lots of wiring. Can you imagine how long it took to wire this thing up? Somebody had to do this all by hand. Wire up all these switches, all the sockets. Wow, lots of time put into this thing. Anyways, on the bottom side, we have an 83 rectifier tube here. So this is a mercury rectifier. And the magic is done with this tube right here, which is a 6BN8. So this is what makes this tester a dynamic mutual conductance tester. The problems with these testers are, and the things that should be changed before you plug one of these things in, are these capacitors right here. Right? These things all go bad. What ends up happening is they usually close, or they end up shorting, in other words. And they cause a lot of problems. So you definitely don't want to burn out this transformer because it's a pretty special transformer. The 83 doesn't have a whole lot of drop across it because it's the mercury variation, and you know, if something goes wrong, one of these capacitors does short, you know, this thing is going to really pull a lot of current. All right, so 83 is a really neat tube, an old 4-pin tube, but it is a mercury type rectifier. There's another capacitor here that needs to get changed. You can see it hiding down here. So in order to remove these tubes, by the way, they've got these spring tabs on them. right? See these little tabs right here? So what you do is you press each side first to loosen them up, and then what I usually do is I put my finger here and then push on each tab and then just gently rock the tube and pull it out, right? Because what it does is it bites on each side here. See that? See how it bites on each side of the socket here, or on each side of the base? So that's because these things were designed to go mobile, right? And you can see the 6BN8 has a nice little holder as well with a spring over the top of the tube to hold it in. Again, these things were thrown in and out of service vehicles all day long during, the television repair time. So, and even radio repair time. So lots of these things have got mileage on them. I'm really surprised to see that this one here looks all original. So you can see there's another capacitor down here that needs to be changed. So this one needs to go, this one needs to go. The ceramic discs can stay. So these capacitors are fine. They're very dependable. Very rarely do they fail. I have seen them fail, but it's very, very rare. In fact, one of the only times I have ever seen a ceramic disc capacitor fail like this is in one of the most dependable pieces of electronic test gear that you'll ever find. It was a Tektronix 547 oscilloscope. Dead shorted. Anyways, so that was the only time I ever come across a capacitor that, a ceramic disc that went bad. It wasn't even high voltage either. So this one has to go, and this one here on the meter. This one here has to go. Other than that, hopefully everything is good. So give the switches a good contact cleaning spray. So use your favorite contact cleaner, hose it down and move the switches a bunch of times. And you can do that with the VRs as well. The moment that you stick a screwdriver in there and move that, you're definitely in for an alignment. So I will clean everything out inside this thing and get everything happening here. So what I'll do, first of all, the very first thing I'm going to do is replace these caps. I'll get rid of these caps and we'll test them for the fun of it, and we'll move on from that point. Removing this capacitor looks relatively easy, so I'll get to that right now. One thing I should mention, this is a vacuum tube tester, and vacuum tube devices run at elevated voltages. There's a reason that this capacitor is rated at 250 working volts. So if you're following along, you're doing so at your own risk. Know the risks of working on vacuum tube gear. Make sure the capacitors are safely discharged. Now this thing hasn't been plugged in years and years and years, and I did measure the capacitors anyways, and they are all discharged. So this is definitely safe to work on. So in order to get at this lug here, what I need to do is move these resistors out of the way. Looks like somebody's tried to solder the insulation on that wire down there. So I need to get to this point here and to this one here. So I'll move this wire out of the way so I don't burn it. Get my iron here and heat this up. This looks like it's just poked through the terminal tie strip. Is it? Or have they put a loop on it? From this angle, I cannot tell. Looks like they did put a bit of a hook on it. So what I'll do is go grab something to remove the hook. I wasn't expecting that. So why they would put it through there and put a hook on it is kind of bizarre, but anyways. Get rid of that. Like so. There, that comes out just fine. Alright, so there's that end. I wonder if they've done interesting things up at the top here. So that looks like the cap right here. This looks like the lead. And I think I'm just about there. There it is. Just like that. 20 microfarad, 250 working volts. This will be replaced with a 22 microfarad capacitor. The way they rated the capacitors way back when is they usually went with just, 10, 20, 30, 40, 50, whatever microfarad. Nowadays it's, 22 microfarad, 33 microfarad. So 22 is absolutely fine in a place like this. It's just a filter. Now these capacitors, look at this. The seals on the ends are fine. I think this thing has very low time on it. Now, don't get me wrong. I'm not saying that, I could leave this thing in and trust it. This was put in and most likely in the 1960s. So if that's a date code, I don't know. Maybe that is Could be, 65 or 76, I don't know. But anyways, these were around in the 60s. That's when these things were made. So yeah, I wouldn't trust this. So no matter what, even if it was in the 80s, early 80s, I wouldn't trust these capacitors at all. And you shouldn't either. So, again, the last thing you want to do is burn this thing out. So at any rate, so let's test this thing and see what it tests as, see if it still is okay. All right, let's test this capacitor and see what happens. There it is right there. All right, so we'll take this lead here, put it here, grab this one here, there, hold it like so. All right, and hit go. So roughly 18 microfarad, an ESR of 2. So that's not too bad. Not too bad. It's doing pretty good for way back when. All right, let's test it for leakage now. All right, let's test it for leakage here. So got everything kind of set up and ready to go. I even have it in the test position. So let's see what happens here. It's hooked up, as you can see. That is a good capacitor. I'm beginning to think that this thing wasn't even turned on. Look at that. Passed the leakage test. I'm beginning to think that this device has extremely low time on it. That test's very good. Very, very surprising. Very surprising. So anyways, the others are probably going to be the same. Would I trust them? Again, no, because they're extremely old, and I'm going to be using this as an active piece of test equipment. So they will all go anyways, but it's kind of fun to see, an old capacitor still working that well. ESR, capacitance, and leakage is all A-okay with this thing. I'm about to install the new capacitors, and way back when, due to size constraints, this is the reason that they installed this way over here. This is just a filter capacitor. Well, this yellow lead runs down under here, and then right over through here, this yellow lead down here. So give you an idea here, you can watch this yellow lead over here. You'll see it being moved. So I'll put my pliers down in here, grab the yellow lead. You can see it moving over here. See that? So that yellow lead runs right up to this portion of the tube socket right here. Okay, so I'll zoom into that. Let's move the camera over here a little bit. So you can see that yellow lead right here. So there's no reason for me to have to install that capacitor way over there. I can install it right over here because this is nice and small and it'll fit right in here. So what I'll end up doing is I'll put this capacitor right in here like so, just like that. Now, you might be thinking, well, maybe they did that because of heating and everything. Well, these bulbs here barely light up and they don't even get warm. I can put my finger on this at any point in time and it's just gently warm, right? These are, I believe, number 55 bulbs. These bulbs are critical, by the way, to the operation of this tester. So if these bulbs are burnt out, you can't just put a 47 in there or something like that and think that everything is going to be fine. It has to be this exact bulb. Again, this has to do with the calibration of the actual tester. All right, so at any rate, I can put this one in here and I can fit the replacement for this one right down in here as well. It's smaller, and when you're looking at the 80 does get pretty hot, right? This tube does get nice and toasty, but you can see it's by the base of the vacuum tube, right? So this is way down here, all right? So if you look at the side, the side of the tube, the capacitor's right about here, right? The hot area of the tube is right up here. This is where it really gets warm. So there'll be absolutely no problem. And again, they're not thinking of heat, they're just thinking of size. And what tells you that, right off the bat is, look, They have this capacitor in the hottest area that it could possibly be in. You know, it's right underneath the plate structure and the filament structure of this tube, right? So that technically that, you know, that's right here, you know, underneath it. Nothing to do with heat or anything. The only reason they put the placement of the capacitor over there, again, is just because of the size of the device, right? You know, where would you put that in here, right? And where would you ground it, right? So now the nice thing about doing this is I can keep the capacitor right close to the diode in the tube, and I can ground it directly to the socket as well. So in a sense, you can look at this like, really, it's improving the design. And it's as easy as that to improve the design. You're putting the capacitor directly close to the rectifier tube, grounding it close to this point right over here. You know, it's a really good idea. Now, there's a really long run of wire over here to this over here, to the switches over here, right? It's a very long run of wire. And it goes in here to the switching, and then when you push the switch, it does go through a whole bunch of other circuitry. So what I'm going to do, as well as adding the capacitor here, is at this point here, I'm going to put a decoupling capacitor at this point. So I'll add a 0.1 microfarad capacitor from here to here. And that will add nice decoupling at that point. You've got to remember you're pushing a switch in and out at this point, and there is, you know, lots and lots of wiring here. So this whole tester could have been improved by a whole lot more decoupling. Like, I mean, you can see that they've added ferrite, basically beads on all of the wiring in here. You can see little ferrite beads. I'll zoom in on that, right? Right, and that's to, you know, basically try to stop any oscillation that might happen. Now, whether they just put these on here as a safeguard, or whether they've put these on here because they actually did experience issues. You can see there's one here, there's one over here. They're all over the place in this thing. If you look over at this side here, they're, you know, they have ferrite beads all over the place, right? So, right, another one down in here, they're all over. So, you know, that in a way is a form of decoupling. You could look at it like that, right? You know, they're putting that in there to most likely stop oscillation, right? So they're all over the place, all over this thing, so I figure a little bit more decoupling couldn't hurt. So if you are working on a tester like this, this might be something that you might want to consider. Put the capacitor closer to the actual rectifier. Again, that's just improving the design. Right? So both of these will be here. Another thing that you're going to need to note is this one's backwards because this is on a negative supply. So the positive of this capacitor is going to the chassis and the negative is going to the tube socket. Again, this is a negative bias supply, so don't put that cap in backwards if you're replacing it, or you'll destroy one of the little diodes in here. So there's two diodes and a triode in the 6BN8. Neat little tube. So you can see the diode structures in there. The diodes are these structures on each side. So that's the diode there. And then on this side, that's the diode. And right in the center is a triode. All right, so if you were to look at this through modern eyes, technically that would be maybe a 1N4007, a 1N4007, and then you would have a JFET in the middle. So that's basically how that would look. You know, you could look at, there's three devices inside this, two diodes and a triode. So depending on the way you want to look at it, maybe an early IC without any other components, right? So we're trying to reduce the size of vacuum tubes way back when, so they were making, you know, multi-element tubes, and of course they went into compactrons and everything way back when. So the compactron is what fits in actually the socket right here. You can see that only the filaments are wired. Pin 1 and 12 are most commonly or pin 1 and 12 on a compactron socket is most commonly the filaments for a compactron. So they've wired the filaments, but they've left all of these open. So if you wanted to wire this to some particular tube that you wanted to test, you have that option. That's the reason that they put this little plug in here. So they were nice enough to do that. And you know, if you were very, very careful, you could actually even put another tube socket in down here. You know, say you wanted some form of a, you know, Novar socket or something like that in the bottom there, or you had some odd tube socket, maybe an 807 socket you wanted to put in here. An 807 is a 6L6G really with a top cap on it. You could put a tube socket in here and then, you know, label the testing for, you know, a 6L6. You could use the same testing for a 6L6 that you would use for an 807. So that's a 6L6G, not the GC version. The GC version had higher dissipation ratings. But anyways, enough of that. Another thing I did notice as I was looking around here, because I'm trying to spot places to improve the design and move things closer and all that, I did spot what looks to be a little bit of a crack on the bottom of this resistor here. So, and I noticed it did look a little bit pale for an Allen Bradley resistor, so it could have gotten hot at some point. So we'll see if I can maybe zoom, and maybe you can actually see it right there without me having to do some camera work. See right there? Looks like a crack. Or a split anyways. So I'm like, I wonder, you know. So at that point, what I did is I got the ohm meter attached. So that should be 390 ohms, okay? So I'll put that right up there. I'll clip this across that resistor. And we'll wait for this to settle off. And look at that, we're at 475 ohms. And that's supposed to be 390 ohms. Hopefully I didn't say K ohms, it's supposed to be ohms. It's 390 ohms. 3.9 and brown, so 390 at 10%. So again, that's gone past the next value. The next value up actually is 470 ohms. So it's actually gone one complete value up plus. So that resistor has to go. So I'll replace that one as well and get rid of that thing. So I'll get rid of all the capacitors here, and when I come back, if I change anything else in the design, I'll let you know. So if you have one of these things and you think you'd like to improve the design, there might be some ideas for you there as well. So I'll get all of this done and I'll be right back. All the new caps are installed and the thing is ready for alignment. In fact, I sprayed everything down already and let everything dry up. The thing was pretty soaked with contact cleaner. There's lots of switches in here. So there's a cap here. There's a cap there. There's quite a bit of space between these two. I can stick my fingers between the resistor and the cap, so they're not touching. It's just the angle that the camera is on. The resistor is replaced. If we take a look at that small capacitor down here, that replaced this very large capacitor right here. That's much further away and closer to the chassis. So these are all 105-degree rated capacitors anyway, so quite a ways away, and it's closer to the actual tip of the bulb here. So no problems with that one whatsoever. Quite an improvement right there. So if I move this out here, you can see the bypass capacitor that's been added right over here. And there's a capacitor that's been added on the meter as well. So this one here was replaced with this one right here. So that's all been done. Again, everything's been cleaned, sprayed, and moved around. So all these VRs are going to be in a different position. Multiple sprays, so spray and then move the contacts a whole bunch of times on the front side and then spray it again. And I usually do that with this standing up like so. So I'll do this with this standing up, and that way I can move all the buttons in and out multiple times, and that way the cleaner doesn't run into the meter, run onto the back side of the meter face and things like that, things that you need to think about when you're spraying a whole lot of contact cleaner. So, lots and lots of contact cleaner, multiple sprays. So you spray, you move the switch a whole bunch of times. These go 360 degrees. They'll keep going clockwise or counterclockwise. So you just keep turning them. And then I turn them the other way, spray them again, and then turn them, and then turn them. So they'll, they keep moving, which is nice. This one here doesn't. This one has a stop at the end. So you move this up to the top, and then you have to move it around a whole bunch of times. And then, just spray everything down and clean it up real good. All the switches have been cleaned. Again, I saved you from that. Lots and lots of videos just about contact cleaning and VR cleaning. In fact, I've done a few myself here in the past, so it's a very simple process. Just use a good quality contact cleaner and you'll be good to go. Again, this looks like a relatively low mileage unit. A lot of the times the paper on the transformer is discolored and things like that as well, so this looks, relatively new. So these are the caps that came out. For the fun of it, this one here was good. So let's test this other one here. It was either that one or this one. No, this one was the one that was good. And this one here was the one that I just removed. So this one here has already been tested. So for the fun of it, let's test this one here and see how well it performs still. So I'll move you up over here to the Genrad. Pardon the camera movement here, lots of movement. Right over there. And I'll zoom you in. And there we go. All right, so let's attach this cap right here. Doing this mid-air. There we go. So there it is, it's attached. The other 20 microfarad, 250 working volts. So this was in the negative supply, this one here. So I'll just put this down, let it focus on that again, and I will hit go. Uh, 21.8, pretty good. ESR is a little bit high. So, not bad, you know. So I'll get rid of that one. So not too bad. So this one here, if I can get this in a little focus square, there it is. Not bad. Paper on them is really nice. Now I save all of these old caps. One day, you know, I might restuff the capacitor, put a new capacitor inside. So I always save these because you never know. A lot of people just throw these things in the garbage, and then one day down the road, somebody that's very specific about a restoration says, I would really like it to look original. And there's some pretty easy ways of doing that with these. So you actually cut the can out, take the guts out inside, and you leave the end caps on. So they look exactly the same way. You just put the new cap inside. Basically just a cap here and a cap here. Works very nicely. So one day I'll do a video on capacitor restuffing and I'll show you my techniques. I don't think I've done one of those yet. Okay, so here's the next one. Focus square, there you are. 10 microfarad, 35 working volts. Planet. Let's see what this one has to say for itself. All right, so I'll attach this off camera here because that's more within my reach. Okay, you can see that right there. It's all attached. And I will move this out of the way and hit go. So that's 38 microfarad and an ESR of 1.8. Now the rating on this capacitor again is 10 microfarad. So why 10 microfarad? So why do we have 38? Well, that's a hint to tell you that the capacitor is leaking inside. So this capacitor here would be leaking. A lot of people seem to think that that means that the capacitor is an overachiever. Well, no, it's not. It's leaking. All right, so let's see what the one that was across the meter is like. So far we've got one pretty bad capacitor. So this is the one that was across the meter. So this is 200 microfarad at 6.4 volts. I don't know if you can see that. It's a little closer here. There's 6.4 volts and 200 microfarad. Okay, so let's see what this one does. So here we go, hooked up and go. So 261. And the ESR is really good. So chances are this one here is leaking a bit as well. All right, so, you know, I guess 50% we're doing okay. The main filters were okay, and that's what really harms the unit. So the two big capacitors are okay, but this one here is definitely not okay. For the fun of it, let's just test it for leakage. Let's see if it's leaking. I suspect it most likely will be. So I will sweep you, pardon the camera movement again. Right there. Hey, look, it's the same level too. That's nice. I'll probably end up moving once I turn everything on here. All right. So this is on electrolytic, and I'll just put this right on to test. Okay. And that way when I connect the leads up, it'll just test it that way because I'm reaching right across the bench here. So here we go. You can see that's the red lead hooked up there, and then this is the black lead right here. Are you going to see this? Probably not. Okay. All right, so here we go. I'll just put that down. Get my hands out of the way. That should already be green. That's 10 microfarad. For a very good capacitor, that would have already passed the test, and it's stuck on that red LED right there, so it hasn't even got off the very, very bad scale. All right, so there it is, right? If it'll focus here, there we go. So there it is in the test leads. And I'll remove the test lead here. So there you go. Very bad, very leaky capacitor. So that would definitely cause problems. And of course, the other one that was on the meter would have caused issues as well. So there you go. I'd say about 50-50. You know, the main filters that would have really caused the damage in this thing weren't bad. So they're okay, I would say. You know, again, I wouldn't trust them. You see this same red capacitor and it's faulty. Now, mind you, that one was baking underneath that 83. So, or on top of it, I should say, when this is back in the case. So, yeah, definitely. Don't forget to change the caps. Don't let anybody ever tell you different. Don't let people try to tell you that you should reform those old capacitors. It's just not worth it. You know, you're taking the chance with a power transformer, which is worth a lot more than, you know, a few dollars for a replacement capacitor. Some of you might want to see the actual comparison between the brand new capacitor. So this is 10 microfarad at 50 volts, all right? So take a look at the meter here and how quickly this moves with a brand new capacitor on it, all right? So I'll just attach this, put this here, and okay, so I'm about to attach this. You'll see the lights move immediately as soon as I attach this. Hard to do this from this far away. So here we go. That's what a brand new capacitor looks like on this meter. So there you go. Anyways, if you're interested in building one of these things, I have all the plans on Patreon for that little capacitor tester. There's nothing out there in production like it, so it's something that I've created, and it works extremely well. You'll see it used in many of my videos, and of course there's complete explanations on how it works and how to build the thing up on Patreon. It's a low voltage leakage tester. So instead of using the high voltages to test the capacitors, this uses a relatively low voltage to achieve the same result, and it's much, much safer than the old Heathkits and Jacksons and things like that that, you know, apply as much as 600 volts to a capacitor, right? Anyways, let's get on with the alignment. All right, let's power this thing up and see what happens. So hey, have you ever seen what an 83 looks like when it comes on? So for those of you that are used to looking at normal tubes when they come on, this tube would probably scare you. So this tube here is a mercury-filled rectifier, and when you turn it on, you'll start to see the mercury form on the glass. So here, I'll just turn this on. All right, we'll see the filaments light up. And if you watch closely, you'll see mercury start to form on the glass. Looks like getter compound actually, but it's a nice big chrome spot showing up. So reflective, I can wave in the reflection there. So now in a normal tube, if a normal tube did something like this, there would definitely be something wrong with it, right? So a gassy tube will normally look like what you see here. You see how it's kind of in that area, how it's kind of hazy. You see a chrome spot here, and then you see a chrome spot over here. I don't know if I can reflect myself in that one, but you'll see a chrome spot on the other side as well. But the haziness in the middle, if a tube looks like that, is usually gassy. But this is normally what a mercury rectifier looks like. And the reason that they're using an 83 in here is because it's much like a solid state diode. There's very little drop across that. So there's very little drop across mercury rectifiers, and it's great in an application like this. It's a very predictable rectifier, so they usually hold out for the duration The failure point of a rectifier like this is usually the filament opens and then they just stop working. Now, a lot of people will talk about these and they'll say, oh, you can replace them with diodes, and that's absolutely fine. Why bother? If the 83 works, who cares? Just leave the thing in there. It's more original, and you have another tube that has to warm up on the other side anyways, so may as well just leave the thing in there. I'm about to perform an alignment on this BK707 Dyna-Jet tube tester. That involves me being around the open circuitry here, and vacuum tube equipment has elevated voltages, which are dangerous. So if you're following along, you're doing so at your own risk. If you don't feel confident in what you're doing, or if working on equipment like this scares you or worries you, do not work on this stuff at all. If you're unfamiliar with this type of circuitry, you might want to familiarize yourself with vacuum tube equipment before you actually try to do an alignment like this. Again, it can be dangerous. You definitely don't want to come in contact with the circuitry at all in any piece of vacuum tube equipment, whether it's a tube tester, a guitar amplifier, a radio, a television, any type of test equipment, anything like that. Anything that has vacuum tubes in it usually has elevated voltages, sometimes known as B+. Be very, very careful if you're going to work on stuff like this, and in fact, I suggest that you don't if you're unfamiliar with this and you're not confident. So now that that's out of the way, in order to align something like this, you need 3 resistors. So you need a 6K ohm resistor, and I believe they wanted 10 watts. I've got 2 12K ohm resistors here in parallel, which makes 6K. Almost spot on the meter too, 6.03 or something like that it turned out to be. So this is 6K ohms. You need a 1 meg ohm resistor. It looks like this right here. And you need a 20 meg ohm resistor. Now, if you got 22 meg ohms or 18 meg ohms or something like that, I wouldn't be too worried about that. In fact, they say in the manual that if you want to increase the sensitivity, you can use a 100 meg ohm resistor, and that way it'll sense grid emission just a little bit more on a sensitive scale. All right, I wouldn't really want to go that incredibly high. I think a 20 meg ohm resistor is the way to definitely go. Now, most of all the testing here is done on socket number 1. So you can tie into the pins on socket number 1 with alligator clips if you like, or you can tie in with a pre-made jig like I have here. So the colors of the wires correspond to the pins. So brown is pin 1, and then we see red is pin 2, yellow is pin 4, and green is pin 5. Now, pin 2 on this socket here and pin 7 are the same, so they'll tell you to tie to either one. You don't need to include, if you want to make a jig like this, you don't need to give yourself 2 grounds, right? So number 2 is just the ground on this one, which is the red lead. So I'll show you what I mean here. All right, and they don't explain this in the manual, but if you look at the socket, it's pretty easy to see. So I'll zoom on into this. Line cord here. The line is off right now, by the way, and the capacitors are safely discharged. I'm not poking my fingers in here with anything charged up. So you can see that this one here is tied to the chassis right here. And then you can see pin 7 over here is also tied to the chassis. So they both do the same thing. So you don't need to have 2 grounds coming out on your test jig. All the rest of the wires are definitely needed though. So in order to start this test, I need to plug this into the front, and I will have this exposed. And of course I'm going to have to tip this thing up while I'm doing this in order to press the buttons and look at the scale and things like that. So what I'll do is I will move you back out here. And I'll plug this into socket number 1. Hopefully this is going to be in the frame. Of course it's not. I'll just put this down like this so you can see me do that. So I'll put this in here. Just plug that in. So that's plugged into socket number 1. That is a loose fit. I don't know. Socket number 1 might have a lot of time on it. I might need to actually tighten the pins on that. That is a pretty loose fit. Usually they should fit quite a bit tighter than that. That's very loose. I might actually have to hold that. So in fact, you know what? I might do that right now. I think I'm just going to tighten up the pins So by sticking a small little screwdriver in there, jeweler screwdriver, I can squeeze the pins shut, and that should make this quite a bit tighter on my jig. All right, I'm about to start the short sensitivity adjustment here, this portion of the alignment. So first of all, it says, to adjust the short lamp sensitivity, connect a 1 meg resistor from pin 2 to pin 4 of socket number 1. All right, so that'll be connected in these leads here, and socket number 1 is nice and tight now. I just basically put a small jeweler screwdriver in there and gave the socket a bit of a twist, and it tightens the pins up inside, so that worked out quite nicely. Adjust R16 while the shorts button is depressed until the short lamp just lights. Now this is a short lamp here, and it's a neon bulb, so they kind of just, I guess you could say, strike, and then they come on. So they don't come up slowly like an incandescent bulb. It'll be off, and then all of a sudden you'll see it, a little bit of orange show up in there, and that would be when it just lights. R16 is accessible with a screwdriver from the top of the panel through the center of socket number 30. That's the socket right here. So I have an insulated screwdriver. So what I'll do is I'll put this down through here, and I'll very gently, you don't want to push because that VR really isn't supported very well under there. So just drop it, and it kind of fits on top, and then very carefully rotate the insulated screwdriver until it falls into the VR, and now it's locked into place right now. So now if I turn it, I'm turning the VR. All right, it says remove the resistor and the shorts light should then go out. So I'm not going to remove the resistor because I don't want to be touching any leads with any B+ possibly applied. So what I'll do is I'll just unplug this rubber insulated socket, and that shorts lamp should go out. So it's not on right now. Everything is unplugged and discharged here. So it needs to go from pin 2 to pin 4. So red is the color 2, and yellow is the color 4. So it's going to go through there. So I'm going to just leave that like that. So that's the 1 meg ohm resistor here. So what I'll do is I will turn on, plug this back in, and turn this on. And is the thing on? Oh, I have it off here as well. There it is. Those are those number 55 bulbs. Again, those are very specific. So you have to wait a few moments for the tubes on the underside to warm up. So we want everything, you know, the rectifier and all the tubes to be in emission and everything like that. What I'll end up doing is, after I've done this alignment here on camera, I'll probably just do it all over again. I'll let this thing warm up for a set period of time, and then do the alignment over again. All right, that rectifier is going to be in about now, and I'd say that tube should be okay. So now what I'm going to do is just press the shorts button here, and as you can see, it's lighting just a little bit. So what I'm going to do is I'll focus you in closer to that point. Hopefully you can see this. So what I'll do is I'll press the shorts. You see how it's lit? So I want to turn the shorts LED or neon lamp off. Getting brighter there. Oh, see now it's off. So now I want to turn this very slowly just until it just strikes. There, it just strikes right there. And that's adjusted. Just that easy. The shorts lamp is out. Everything is still attached as it was before. You can see the resistor still in there. I will press the shorts button. Now my finger is not touching the chassis at all. I'm just touching the shorts button. This is rubber insulated as well, so I'm doubly protected here. Now when I pull this out, that shorts lamp should go out. There it is. And that is the final portion of the shorts test. The next portion of the alignment is the grid emission sensitivity adjustment. So it says here, the sensitivity of the grid emission test circuit is adjusted at the factory so that a leakage of 25 megohms just reads in the grid emission reject area on the meter scale. This order of sensitivity is the level that tube manufacturers recommend in order not to reject good tubes. Well, makes good sense, right? Unlike those crooked grocery store vacuum tube testers, right? The grocery store people would get in there and screwdriver so that every tube was bad. I have stories. Anyways, to adjust the grid emission sensitivity, connect a 20 meg resistor from pin 1 to pin 7 of socket number 1. So I'm saving some time here by getting this done. So now, if you recall, pin 7 is the same as pin 2. right? They're both grounded, so I have it going from pin number 1, which is brown, to pin number 2, which is absolutely fine. All right, so let's see here. Adjust R18 while the grid emission button is depressed. Let's see here. Looks like, is that a period there? For a meter reading of 20 on the numbered scale. R18 is accessible with a screwdriver from the top of the panel through the center of socket number 33. Remove resistor. Meter reading should fall to 0 with nothing plugged into the panel. And then here it is with a 100 meg resistor explanation. If you want to make it more sensitive, you can just basically put a 100 meg resistor in there instead of a 20 meg. So it says here, if you wish to make the grid emission test more sensitive, use a 100 meg ohm resistor in place of the 20 meg ohm resistor as stated above. I wouldn't do that because you might get more rejects for no reason. All right, so socket number 33 is here. So I'll put this down here and very carefully try and lock that in. It feels like it's locked in there. I think this one here is a little bit, might slip out a little easier. So now what I need to do is, first of all, I should mention that this needs to be mechanically zeroed. All right, so this mechanically zeroes it. Before you want to do any readings on this scale, make sure that with nothing else happening, that this sits right on the 0 line. So if this is sitting above the 0 line with nothing plugged in and no buttons pushed, you need to mechanically zero it with this little screw here. Very carefully put a screwdriver in there and move that, and you'll mechanically zero it. And after that, the meter should be accurate from that point on. It also will need to be on a flat plane in order for you to do that. If you do it standing up, it will be off a little bit. When you lay it down, it will move again, all right, just because of the weighting of the needle. So make sure it's laying down flat, kind of like it is in the tube tester when you're going to use it, right? So it says here we need to press the grid emission. Oh, wow, that's way up there. Okay. So let's see here. So we need to move it to read to the number 20. Come on, you can do it. That is very sensitive. So it comes in very, very quickly. I'm just touching this. So now the camera is on an angle to this, so I'm going to have to kind of look over this and see it come down to the 20 mark. Wow, that is really touchy. That is a very touchy setting. And it's the control itself is really tough to move, even though it's been cleaned. It's a really stiff control. I didn't expect it to come in like that. Right there it is, right on top of the 20. To my eyes, that's right on top of the 20. So it might look a little off on the camera, but I was looking straight down at it. So there it is. Now, when I unplug this again, that should fall to 0, which it does. And that's it for the grid emission adjustment. Just that easy. The next portion of the alignment is the signal voltage adjustment. It says to calibrate the instrument for proper signal voltage, connect an AC VTVM to pin number 1 of socket number 1. Connect the ground lead of the VTVM to pin number 2 of socket number 1. So basically you're just grounding the VTVM to pin number 2 of socket number 1, and the signal is fed from pin number 1 into the VTVM, so into the AC probe. I'll talk more about that in a moment. Adjust R20 while test 1 button is depressed for 1.5 volts RMS. R20 is accessible with a screwdriver from the top of the panel through the center of socket number 25. And this here is socket number 25, so I will put this through. Since this is out of the case, I can look on the side here to actually see if it's aligned very well here. If I've got the screwdriver into the slot there. So now I have a VTVM back here. All right, I will zoom in on that. Now you can get away with using a DMM for this as well. They want a VTVM used, so I'm just showing the actual, VTVM being used. So now this is just a voltage that's floating there. Another thing I want to mention, which is a really good safety precaution, is put the sensitivity adjustment right here down to 0 first. So you'll notice that it was up high before. Put it right down to 0. That's just good practice, just to stop anything bad from happening. So you don't want to be pegging out the needle on the tube tester. So not very much anyways. Like, a little bit of a peg is okay, but you don't want to hurt the needle. This one here you'll see slam against the end, but this is protected. So not a big deal with this one. That's just the nature of the beast with this thing when it's in a real sensitive scale. So let's see, where was I? So now I've got the VTVM probe hooked up here to socket number 1. Right now I'm just touching the socket. That's how sensitive this VTVM is. So extremely high impedance there. So what I'm going to do is I'm going to press test number 1. Right, so I'll just back this out for a moment. And get you back down here for a moment. So I'm going to press test number 1, which is right here, and I'm going to adjust this for 1.5 volts, which should be right about here on the scale. I'll show you. And after that, that is done. Again, you can use a DMM for this if you like as well. So when I press this, the needle is going to go kerslam up against the top, and then I'll wait for it to settle off. And then I need to adjust this for 1.5 volts. Okay, so we're using this scale right here. See where it says 3, 2, and then 1 in the red? Okay, so this is, I'm on the 3 volt scale. All right, so I'm going to press test 1 right now. That actually wasn't too bad. When I let it go, I know it's going to probably slam up against the end. So now I need to adjust this VR. I'll twist this till I get right down to 1.5. Now the camera's off on a bit of an angle. To my eye, that's 1.5. Now watch what happens when I let this button go. That's not a big deal. So this is protected. That's okay for that meter to do that. So again, I'll press test 1. And there it is. 1.5 volts. That's me letting go of the button again. So that's it for this portion of the test. Again, while I was doing that, back this out here. I had the adjustment in here, and I was twisting this while test number 1 was pushed. The next step is the DC bias adjustment. It says here, to adjust for proper DC bias, connect a 20,000 ohm per voltmeter between pin 1 and pin 2 of socket number 1. Adjust R11 while test 1 button is depressed for negative 2.5 volts DC. R11 is located beside the 6B and 8 tube on the transformer bracket. So R11 is that VR right there. Now you might be wondering, why does it say use a 20,000 ohm per voltmeter between pin 1 and 2, right? That's quite a change from a VTVM. Well, here's the reason. When you let the test button number 1 go, the voltage will soar up to about 80 plus volts. And then when you press the button down, it'll go down. All right, so what ends up happening is it ends up pegging the needle on the VTVM because it's so sensitive, and it could damage a VTVM. All right, you saw how the needle was pegging before. Well, that was just, the voltage was just going beyond 3 volts just a little bit. It's actually going up to about 11 or 12 volts. Now this is going to go from negative 2.5, really to 86 or so. So that's not very good. And what happens, because this is 20,000 ohms per volt, in the 3 volt position, what is that? Well, that's 60k ohms, all right? And what that's doing is it's loading down the circuit, so the meter isn't actually pegging out. Now, it's absolutely fine to use a regular DMM, digital voltmeter, any type of multimeter for this particular adjustment. You should be absolutely fine. You'll notice when you let the button go, the voltage will soar, so watch that, all right? And definitely don't touch the lead. So I'll show you what I mean here. So right now, you can see that with this meter, if I zoom into that, with this meter here, we're on the 2.5 volt, or on the 3 volt scale, I should say here, on the 3 volt scale. So that's 3 volts at the top, my arm isn't in the way, and you can see that we're just under 2 volts there. So the top scale, that's 3 volts, 2.5, and 2 volts right there. So now, if I go about moving the probe leads from this meter here, I'll unplug the probe leads. Unplugged from the other thing there. I'll unplug the probe leads here, and I'll plug them into my other meter. Of course, everything is tangling up as I'm doing this. This is what we're getting on the DMM now. Right up here. 87 volts. Now you'll see that it was under 3 volts on the other meter because the meter's loading it. So that's 87 volts right there. So, of course, at a reduced current, but it's still, 87 volts. And then, of course, I'll press number 1. See how close we are to the actual reading. We're actually not far off. 2.5 is where it's sitting. So I'll let the button go again, and you'll see it goes right back up to 87 volts. So now, I'll plug these back in here. So I'll move you down to the meter. Move you down to this meter right here. Okay. Back that out just a little bit. And so I got this here, so I'll put the common in here, and I'll put the other probe in here. And as you can see, again, we're below 2 volts, right? So that's how much it's loading it down. Now, when I press the button, we should actually get an increase on the screen here. All right, so there we go. That's 2.5 volts, close enough. This is going to move around as it heats up a little bit too, So things will move up and down here, but that's right at 2.5 volts to my eye. And that meter is very correct, so no problems with that. Again, there will be a slight bit of drift. These things need to warm up. So what I can do here is I'll show you the adjustment here. I'll pop the screwdriver, my insulated screwdriver, into this VR down here. So I'll move the meter here for a second. So I'll pop this into here. And go in from this side, it doesn't matter. Go from the insulated side here. Okay, so I'll give this a twist here while I am pressing number 1. Okay, so move you back up to the meter here, and I'll give you an idea of what's going to happen on the actual scale here. Need to get around on the other side here and get this back into that VR. Okay, so I'll press number 1, right, and I'll move it around. See that? That's just a little bit of movement each side. So, and we want that right at 2.5. Kind of touchy. Right there, 2.5 volts. And that's straight onto my eye as well. So there you go. So that is the DC bias adjustment. One other thing that I should mention just before we move on to the next step, just so I'm as thorough as possible. If you're not used to these meters, you may not know this, but in order to read a negative voltage on a meter like this, you need to reverse the leads. So you'll notice I've got the leads plugged in normally here, but where they're attached to the tester, the test leads are actually reversed. Now this is completely isolated. This is a standalone meter. There's no power to this whatsoever. So I've got the positive lead of the meter attached to the ground. And you can see I've got the negative lead of the meter here attached to where we're going to read the voltage in order to get a negative reading. So if you're trying to read a negative voltage on this, obviously what's going to happen to the needle? Well, it's going to want to go this way. It's just going to hit the stop. So you need to make the needle move forward. So in order to do that, if you're reading a negative voltage, you just reverse the leads. This is common knowledge for anybody that used to use these old meters, but if you're not used to a meter like this, that would be relatively new to you. So hopefully that helps out and helps your understanding of the way these older analog meters work as well. We're now at the final portion of the alignment, which is the balance control adjustment. So I'll zoom you into this here. It says, to adjust R5, connect a 6,000 ohm 10 watt resistor from pin 5 to pin 2 of socket number 1. Set sensitivity control to 100. Adjust R5 while test 1 button is depressed for 0 reading on the tube tester meter. R5 is located on the rear of the transformer mounting just behind the power transformer. So that is, if I tip this up, I'll back you out here so you can see it's underneath here. It's that one right there. So we just adjusted this one. Now we need to adjust this one right here. And in order to do that, I have a very long insulated screwdriver, and I will put this over here, put that into the VR right here. So that is now resting in the VR. I'll show you what I've done here. So it's just resting in the VR right there. Now what I need to do is plug the 6,000 ohm resistor in. So this is going from pin 5 to pin 2. This is 6,000 ohms here. And I will just plug this. The reason I have it unplugged right now is because I had to tip this thing up. Just plug that in right there. Now I need to set the sensitivity control to 100 and adjust this for 0 while pressing test button number 1. So what I'll do, just to make sure the meter is safe and everything is going okay, is I'll advance this from 0 to 100 while this test is pushed in, just in case something's wrong. I don't want this to peg out. All right, so I'll move this up. And as you can see, it does need adjustment. All right, so that's at 100 there. So what I need to do is, while pressing the test button, number 1, I need to bring this down to 0. So let's see which way is 0. This way is 0. And if I get right over top of it, well, that's right on 0 right there. Perfect. So that's right on 0. So that's the last portion of the alignment right there. Another thing that's worth mentioning just before we go about testing a tube with this, before you put this thing back into the case, there are a lot of standing components on the bottom side here that can be bent all over the place. And a lot of these are heat generating components. So if you see right here, you'll see these two large resistors. You want to make sure that they're not squished down on any wires or anything like that, right? You want to stand these things up and make sure that there's room between them so that they can breathe. So, and that goes for all of the resistors on here. There's quite a few larger resistors on here, and they'll very easily get pressed down like this, and they'll lean on wires while you're changing components, because as you're working in here, you bump things with your plier, or you'll press something out of the way to maybe unsolder a lug. So it's very important to remember that. Another thing that you're going to want to do here is, if you've been changing components in something like this or anything, what you want to do is take this thing and give it a few bumps, just light bumps, and then shake it like this too just before you put it back in the case, because sometimes little pieces of wire can hide. They'll get jammed under things and they're just waiting to short something out, right? So there's lots and lots of area in here for little parts and pieces to get jammed, little wire trimmings and things like that. So just a few extra suggestions and recommendations before you go about putting something like this or anything that's point to point back into its case. All right, let's test this brand new 6K6. Look at that nice shiny plate in there. These old barrel plate 6K6s, they sure worked great. So in order to set this up, it's relatively simple. I'll zoom you in. You can see at this socket right here, 29, it says 6K6 92. So what that means is we put the sensitivity here up to 92. I'll move this up. 92. Since the first number in 6K6 is the number 6, we know that's the filament voltage. So we can take this and put that up to 6 volts. Now at this point, we want to make sure that we're on this side. You can see how this neon is glowing. That means that we're on this board right here. On the bottom, you'll see another neon down here. So if I press this switch down, now we're on this particular portion to test in. So we don't want to be down here because we're using this socket, so we want to be up here. So now that we're there, let's plug in this 6K6 and see what happens. So here we go. Rotate that and plug that in. Give it just a few minutes to warm up, a few moments. We'll zoom back in just a little bit right here. See, it's glowing nicely there. right, so let's test it for shorts. I'll press the shorts right here. It's just fine. If there's something wrong, this light here would light up. Let's test for grid emission. So if it's outside of that little green area there, that means it's a grid emission reject. So it's okay. No problems there. So now let's test it. Let's press test 1. Where do you think it's going to be on the scale? Brand new 6K6. Place your bets. Here we go. Wow, look at that. Over 100. That is a nice tube. Now, if we want to give this tube a life test, we want to see how much life is left in it. What we do is we press test 1 and push this spring-loaded switch over to life test. And what should happen is the needle should stay relatively steady. It should stay constant. If it drops back quickly, we know that the tube is used up. So if it stays pretty steady and just moves down just a touch, we know that we're doing okay. Sometimes it'll even move up just a little bit. So here, let's try this. All right, so I'm pressing test 1. Now I'm going to press the life test. Here we go. And as you can see, there's a lot of life in that tube. That tube is going to last a long time. So no problems with this tube whatsoever. We can tell it's a brand new tube, right? You know, it didn't even move. So lots of life left in there. So there's a demonstration of the B&K Dyna-Jet 707 and all of the alignment procedure. Thanks for stopping by the lab today. Hope you enjoyed the restoration process of this B&K Dyna-Jet 707. If you did enjoy the video, you can let me know by giving me a big thumbs up and hang around. There'll be more videos like this coming in the near future. We'll be looking at vacuum tube and solid state electronic devices alike. So if you haven't subscribed, now would be a good time to do that as well. If you're interested in taking your electronics knowledge to the next level and learning electronics in a very different and effective way, and gaining access to many of my personal electronic inventions and designs, you're definitely going to want to check out my ongoing electronics course on Patreon. I'll put the link just below the video's description under the Show More tab, and I'll pin the link at the top of the comment section. So if you click on the link, it'll take you right there. It's a great community, and there's a lot of great projects for you to build and lots of videos there as well. You'll definitely enjoy it. Check it out. All right, until next time, take care. Bye for now.